Welcome to another deep dive. Today we are going to be talking about the element nobelium.
Nobelium is pretty cool, right?
I've heard of it, but I don't really know much about it.
Well, that is what we're here for, to dive deep.
Perfect. So where should we start? I know it's one of the heavier elements on the periodic table.
That's right. It is number 102. It is way down there, past uranium.
So it's one of those transuranium elements.
Yep, the transuranium
I
element.
remember hearing those are pretty special.
Yeah. The thing about those transuranium elements is they don't just exist naturally.
Oh, right. Like you can't dig them up out of the ground or anything?
Exactly. You have to make
How
them.
do you even do that?
You smash other atoms together really, really fast and hope that some of them fuse.
So like an atomic car crash?
Pretty much. Scientists use these massive machines called particle accelerators to get the atoms up to insane speeds.
So they just load up the particle accelerator with like a bunch of atoms and fire away?
Well, it's a bit more complicated than that. You have to choose the right ingredients, the right atoms to smash together.
So for nobelium, what are the magic ingredients?
One way to make it is to use californium-249 and carbon-12.
Okay, so you take those atoms, you get them going super fast in the particle accelerator, and bam, nobelium.
Well, not quite bam. It's actually incredibly difficult to get the atoms to fuse. It's like trying to hit a bullseye from miles away.
So even with all that technology, it's still kind of a long shot.
It is. Even if you do everything right, the chances of creating nobelium are still pretty small.
Wow. Talk about a needle in a haystack. But let's say they do get lucky and those atoms fuse. What happens next? How do they even know they've made nobelium?
That's where things get really interesting. They have to study how the nobelium decays.
Right, because it's radioactive, right?
Exactly. Nobelium-255, the isotope we were just talking about, has a half-life of just over 3 minutes.
Right, 3 minutes. So that means half of it disappears in just 3 minutes?
Yep, pretty much. It decays into other elements.
So scientists have to work really fast to study it before it vanishes.
That's one of the biggest challenges with researching nobelium. It's a constant race against time.
3 minutes.
Yeah.
That's insane. So how do they actually study something that disappears that quickly?
It's all about analyzing what's left behind, the radioactive fingerprint, you could say.
Huh.
By looking at what it decays into and the energy released during decay, scientists can confirm they did indeed create nobelium.
Ah, so it's like a detective story using those clues to piece together what happened?
Exactly. But nobelium's story isn't just about science. There's a fascinating human drama behind its discovery.
Oh, do tell. I love a good science rivalry.
Well, back in the 50s and 60s, the Cold War was in full swing, and there was this intense competition between the U.S. and the Soviet Union, not just in space, but in science, too.
So nobelium became another front in the Cold War.
You could say that. Multiple labs around the world were racing to create new elements, and nobelium was a prime target.
So who was the first to claim victory in this atomic race?
A team in Sweden actually announced they had created nobelium in 1957. They even proposed the name nobelium, which obviously stuck. But there's a twist.
A twist. Ooh, I love twists. What happened?
Well, it turns out they were probably mistaken. Later analysis suggested they might have misidentified another element, thorium-225.
Oh, no. So a false start.
Yep, and with that, the race was back on.
So who took the lead after that?
Two main contenders emerged. A group at Berkeley, led by, you guessed it, Albert Ghiorso and Glenn Seaborg.
Wow, Seaborg himself. That's like the scientific dream team.
It was a big deal. And their competition was a team at the Joint Institute for Nuclear Research in Dubna in the Soviet Union.
So the Cold War rivalry was playing out at the atomic level.
Pretty much. And to make things even more complicated, they were using different methods to try and create nobelium. Imagine two chefs trying to make the same cake using completely different recipes and ovens.
Oh, wow. That's a recipe for disaster, or at least a lot of confusion.
Exactly. There were conflicting results, claims, and counterclaims flying back and forth. It took decades to sort it all out.
So who ultimately won bragging rights?
Well, in 1992, unpack, the organization responsible for naming elements, finally decided to officially credit the Dubna team with the discovery.
So the Soviets got the win.
They did. Their experiments from 1966 were deemed the most conclusive.
But we kept the Swedish name Nobelium.
Yeah, by that point, the name had become so widely used that changing it would have just caused more confusion.
Right. That makes sense. So creating Nobelium was a huge achievement, full of scientific drama and international rivalry. But now I'm curious, what's so special about Nobelium beyond just the challenge of making it?
Well, nobelium has a bit of a rebellious streak. It doesn't always follow the rules you'd expect based on where it sits on the periodic table.
Oh, tell me more. I love a good rebel.
So you know how elements in the same column of the periodic table tend to have similar properties?
Yeah, like they're kind of like families, right?
Right. And based on nobelium's position in the actinide series, you'd expect it to behave like its siblings and prefer to be in what we call a +3 oxidation state.
Okay, remind me what an oxidation state is again. I remember it has something to do with electrons, but
Sure. Imagine each atom as a tiny social butterfly, always looking to make connections by sharing electrons.
okay, I can picture that.
So the oxidation state tells you how many electrons an atom has gained or lost in those social interactions.
So +3 means it's lost 3 electrons.
Exactly, which usually makes it more positively charged, so to speak.
Okay, I think I'm following. So most actinides prefer to lose 3 electrons and hang out as +3 ions.
Right, but nobelium likes to do things its own way. It prefers a +2 oxidation state.
So nobelium is a rule breaker. Why is that?
It all comes down to some pretty mind-bending physics called relativistic effects. Basically, when you get to elements as heavy as nobelium with so many protons and electrons, things start to get really weird.
What?
Well, the electrons are moving so ridiculously fast that they actually gain mass, and that changes how they interact with the nucleus.
Wait, the electrons gain mass. Isn't that like Einstein's theory of relativity stuff? I thought that was for like black holes and stuff, not atoms.
It's all connected. Relativity affects everything, even tiny electrons.
Wow, that's mind-blowing.
Right, so these super speedy mass-boosted electrons in nobelium end up making the +2 state more stable than the +3.
So nobelium's rebellious nature is actually a consequence of Einstein's theory of relativity. That's an aha moment I wasn't expecting today.
It's a fascinating example of how physics and chemistry are intertwined, especially when we get to these extreme elements.
This is already so much more interesting than I thought it would be.
Right.
And we've only just scratched the surface of nobelium's story.
We've got a lot more ground to cover. Next, we're going to take a closer look at the structure of a nobelium atom and the ingenious techniques scientists use to study something that disappears in minutes.
Okay, I'm ready. Let's dive in. All right, so we're going deeper into nobelium. We're going right into the atom itself.
Sound good?
So we know atoms have a nucleus, right? Protons, neutrons, all that.
Right.
But what about the electrons? How are those arranged?
Well, you can't forget about those electrons. They're not just randomly floating around.
Right. I remember those electron shell diagrams from chemistry class, all those
yeah.
wings and numbers.
Yeah, exactly. Each electron in nobelium has its assigned spot based on its energy level, like a well-organized dance floor, you know?
So, like, each electron has its own specific energy and location?
Yep. It's all very precise. And with 102 electrons, nobelium's electron configuration gets pretty complex.
102 electrons. Wow. So how do scientists figure out where all those electrons go?
They use what we know from the periodic table, along with some pretty complex calculations. It's like solving a giant Sudoku puzzle.
Okay, so what's the solution to the nobelium electron puzzle?
Well, we think it's something called Rn5F147s2.
Whoa. Okay, that's a lot of letters and numbers.
I know, it looks intimidating, but it's just a shorthand way to describe the arrangement.
So can you decode that for me?
Of course. The Rn part is a shortcut. It represents the electron configuration of radon, a noble gas.
Okay, so radon has 86 electrons. So are you saying that the first 86 electrons in nobelium are arranged the same way as in radon?
Exactly. It's like nobelium starts with radon's stable electron structure and then builds from there.
Okay, that's a good starting point. 86 down, 16 to go. So where do those other electrons hang out?
Those last 16 are the key players. They determine a lot of nobelium's personality, chemically speaking.
So where do they fit in?
The 5F14 means the 5 subshell is totally full, 14 electrons chilling there. And the 7s2 means there are 2 electrons in the 7's orbital.
And those orbitals, that's where the electrons are actually located, right?
Right. Imagine these orbitals like different shaped clouds surrounding the nucleus, and each cloud can hold a certain number of electrons.
So what about those outermost electrons? Are they important?
Those are super important. Those are called the valence electrons.
Valence electrons, right. They're the ones that do all the interacting with other atoms, right?
Exactly. Like when nobelium forms chemical bonds with other elements, it's those valence electrons doing the heavy lifting.
So those inner 86 electrons from radon, they're just kind of background players.
Well, they're not unimportant. They provide stability to the whole atom, kind of like a strong foundation for a house. They don't directly bond with other atoms, but they influence how the valence electrons behave.
So teamwork makes the atom work. Now, I remember something about ionization energy, how much energy it takes to rip an electron away from an atom.
Right.
How does that play into Nobelium's story?
Well, it relates to that rebellious +2 oxidation state we were talking about.
Oh, right, I was just thinking about that. So, if Nobelium wants to get rid of two electrons, does that mean it's easier to rip those electrons away?
Bingo. Nobelium has a relatively low ionization energy, at least for the first couple of electrons. So it doesn't take a lot of energy to convince it to give up those two and form that No2 plus ion.
Wow, that all ties together nicely. I'm starting to really appreciate all the complexity going on inside an atom, but I have to admit, it's all still pretty abstract for me.
It's definitely hard to visualize. But you have to remember, all these tiny interactions between electrons determine how nobelium interacts with the world, its whole chemical personality. It's pretty amazing when you think about it.
You're right, it is pretty amazing. Okay, well, speaking of things that are hard to visualize, we keep coming back to this whole half-life thing with nobelium.
Yeah, that short half-life is a big challenge.
It makes me wonder, what if nobelium wasn't so radioactive? What if it stuck around longer?
That's the dream, right? Stable nobelium.
Imagine what we could learn if we could study it for, hours or days instead of minutes.
Exactly. It's a big question in nuclear physics. Can we make super heavy elements that are more stable?
So are there any ideas about how to do that?
It all comes down to the nucleus, that core of protons and neutrons.
Right, like those different isotopes we talked about.
Exactly. The stability of an isotope depends on the balance between protons and neutrons in the nucleus.
So, like, some combinations are more stable than others?
Right. With nobelium, the isotopes we've found so far, they all have pretty short half-lives.
But you're saying there could be other isotopes out there, ones we haven't discovered yet, that might be more stable?
It's possible. We just haven't found the right combination of protons and neutrons to hit that sweet spot for stability.
So it's a bit like a cosmic lottery, trying to hit the jackpot with the right number of protons and neutrons.
Pretty much. It's a challenge, but scientists are working on it. They're using particle accelerators to create and study these super heavy elements, hoping to find those elusive, stable isotopes.
So it's a long shot, but not impossible.
Never say never in science.
All right, well, I'm keeping my fingers crossed for stable nobelium, but for now, we're stuck with these fleeting isotopes. So how do scientists study something that's literally disappearing before their eyes?
Well, it takes a lot of ingenuity and some very sophisticated tools.
Like what?
One of the most important techniques is studying the radiation that's emitted when nobelium decays.
Oh, right, because when an atom decays, it releases all sorts of particles
Yeah.
and energy, right?
Exactly. And by analyzing that radiation, like those alpha particles, scientists can actually identify which isotope is decaying and map out its decay chain.
Decay chain, that's a new one. What's a decay chain?
It's like a chain reaction, where one radioactive isotope decays into another, which decays into another, and so on.
So like a whole family tree of radioactive isotopes, each one transforming into the next.
That's a great way to think about it. And by tracing that chain, scientists can understand how the nucleus changes over time, how much energy is released, all sorts of information about the atom's structure and behavior.
Wow, that's pretty incredible. So how do they actually see this radiation? Do they have like radioactive microscopes or something?
It's not quite a microscope, but the detectors they use are pretty amazing. There's a whole variety of them, each designed to detect different types of radiation.
Okay, so like what kind of detectors are we talking about?
One common type is a scintillation detector.
Scintillation. Sounds fancy.
It basically converts the energy of the radiation into light.
Wait, so you can actually see the radiation?
Well, not directly,
Yeah.
but the detector uses a special material that emits a flash of light when it's hit by radiation. The brighter the flash, the higher the energy of the radiation.
So they're converting invisible radiation into visible light.
Exactly. It's a really clever way to study something that's otherwise very difficult to detect.
I'm really getting a sense of how much creativity and ingenuity goes into this kind of research.
It's definitely not your average science experiment, but it's all driven by this deep desire to understand these super heavy elements, even if they only exist for a few fleeting minutes.
So all this effort, all this technology to study something that barely exists, why bother? Why is nobelium so important?
That's a great question, and it gets to the heart of why we explore the unknown at all. It's about pushing the boundaries of knowledge, seeing how far we can go. Nobelium, it might not have any practical uses right now, at least not that we know of.
Right. But it teaches us so much about the fundamental nature of matter, about the forces at play inside the nucleus of an atom.
So it's like By studying these extreme cases, these elements that are barely there, we gain a deeper understanding of how the universe works.
Exactly. It's like we're expanding our view of reality.
I like that, expanding our view of reality. So even if Nobelium never leads to some new technology or solves some world problem, it's still valuable in its own right.
Absolutely. It's about the pursuit of knowledge for its own sake. It's about that human drive to explore and understand the world around us, even the parts that seem completely out of reach.
And it's a good reminder that science isn't just about the facts and figures. It's also about the people involved, their stories, their passions.
Oh, for sure. Like, think about the whole saga of Nobelium's discovery,
Yeah.
the Cold War rivalry, the mistaken identity, the naming controversy. It's a great example of how science is a human endeavor full of drama and excitement.
Yeah, for sure. It's like even at the atomic level, there's still this human element at play. Exactly. And, speaking of that naming controversy, I think it's worth revisiting that because it really highlights how science is influenced by social and political factors.
Right. So remind me, why were the Soviets so adamant about naming it Juliosium?
Well, they wanted to honor Aaron Curie, a brilliant scientist who made huge contributions to nuclear physics. I mean, she and her husband basically discovered artificial radioactivity, which was a massive breakthrough.
Oh, yeah, I remember learning about that. So both namesakes, Alfred Nobel and Irene Joliot-Curie, were super deserving.
Exactly, which is probably why the whole debate got so heated.
So how did they finally settle on Nobelium?
Well, it was tricky. IUPAC initially accepted the name Nobelium since it was already being used, but then there was this huge backlash. Eventually, they kind of compromised. They kept Nobelium, but acknowledged the Dubna team's contributions to its discovery.
So Nobelium finally got its name, but not without a fight.
Pretty much sums it up. It's kind of fitting in a way. Nobelium itself, it's this element that's hard to make, hard to study, always on the verge of disappearing. It's like its story is just as complex and intriguing as the science itself.
That's a great point. It's like a microcosm of the scientific process in general. There are setbacks, controversies, dead ends, but ultimately there's this drive to keep pushing forward, to keep exploring the unknown.
Couldn't said it better myself. And, who knows, maybe someday we'll be back here talking about the amazing properties and applications of stable Nobelium.
Well, that's a deep dive I'd definitely tune in for. But for now, thanks for joining us on this journey into the world of Nobelium. Hopefully you learned something new and maybe even got a little inspired by the power of human curiosity and scientific ingenuity.
Cheers to that.
And until next time, keep exploring.